Greetings to all. I am Dr. M. Sudha, Head and Associate Professor of Mathematics, Sri Sarada College for Women, Autonomous, Salem 16. In this video, we are going to discuss some interesting attributes of connected spaces. It is one form of topological space which is having wide range of applications in almost all fields. First, let us come to the concept. Let X be a topological space. A separation of X is a pair U, V of disjoint, non-empty open subsets of X whose union is X. So what is the separation of a topological space? It is a pair of disjoint, non-empty open subsets of X whose union is the space. Now the space X is said to be connected if there does not exist a separation of X. So you can say a space to be connected if it has no separation at all. Now let us see few examples on connected spaces. Example 1, let Y denote the subspace union of two half-open intervals -1, 0 and 0, 1 of the real line R. Now these two sets -1, 0 and 0, 1, you can very much view from the diagram. These two are non-empty, they are disjoint and they are open in Y. Since the space Y is the union of these two sets, so it very much satisfies the definition of a separation of a space. So Y becomes a not connected space. Since there exists a separation for the given space Y, the space Y is not connected. Next example, let X be a subspace, the closed interval -1, 1 of the real line R. Now this space X can be written as the union of these two sets, -1, 0, the closed interval, and the half-open interval 0, 1. So you can observe from the diagram, these two sets are disjoint and non-empty, and their union is the space X. But since the first set, -1, 0, this closed interval, it is not open in our space X, because in the standard topology, as per the definition of standard topology, this is not open in X. Therefore, though they are disjoint and non-empty and their union produces X, since the first set is not open in X, these two does not form a separation of X, hence X becomes a connected space. Next, let us see a remark. A space X is said to be connected if and only if the subsets of X that are both open and closed in X are the empty set and X itself. So, from this remark, what we observe is, in a connected space, only the empty set and X are alone both open and closed. So no proper subset can be both open and closed. Let us come to the proof of this remark. Let X be a connected space. To prove that only empty set and the whole set X are only both open and closed, let me assume the contrary. That is, suppose that A is a non-empty proper subset of X which is both open and closed in X. Let U is equal to A and let V be the complement of A. Since A is closed, the complement of A, that is our V, becomes open. So now U and V are both open, disjoint and non-empty, and their union is X. Therefore, by definition, U and V form a separation of X. But this cannot happen because X is a connected space. So what we have assumed is wrong. That is, the only subsets of X that are both open and closed in X are the empty set and X itself. Conversely, Suppose that the only subsets of X that are both open and closed in X are the empty set and X itself. To prove X is connected, that is, I have to show that there exists no separation of X. Again, here assume the contrary. That is, suppose that U and V form a separation of X. Then U is non-empty and it is different from X. Also, it is both open and closed in X because U can be written as a complement of V. So U becomes both open and closed. Therefore, U is now a proper subset of X, which is both open and closed in X. This is a contradiction to our assumption. Therefore, what we have assumed is wrong. That is, there exists no separation of X, proving that X is the connected space. Next concept is on connectedness of a subspace. If Y is a subspace of X, a separation of Y is a pair of disjoint non-empty sets A and B whose union is Y and neither of which contains a limit point of the other. And the space Y is connected if there exists no separation of Y. Coming to the proof, suppose that A and B form a separation of Y. Then by definition, A is both open and closed in Y. Even from the previous remark, it is very much clear that A is both open and closed in Y. Now the closure of A in Y is the set A bar intersection Y, where A bar is the closure of A in X. Since A is closed in Y, now A bar intersection Y is A itself. This implies A bar intersection B is empty. This is very much clear from the definition. See, A and B form a separation of Y. This rectangle is our subspace Y. Now A and B forms a separation of Y. Now A bar intersection Y is A. This is equivalent to saying that A bar, this one, A bar intersection B is empty. So you can observe from the diagram. Since A bar is the union of A and its limit points, this B contains no limit point of A. See, A bar, here lies all the limit points of A. Since A bar intersection B is empty, B contains no limit points of A. Similarly, you can show that A contains no limit points of B. Therefore, we have shown that the separation of a subspace is a pair of disjoint non-empty sets A and B whose union is Y and neither of which contains a limit point of the other. Conversely, suppose that A and B are disjoint non-empty sets whose union is Y and neither of which contains a limit point of the other. Now we have to show that A and B form a separation of Y. Now since A contains no limit point of B and B contains no limit point of A bar intersection B is empty and A intersection B bar is empty. Therefore, this leads to A bar intersection Y is A and B bar intersection Y is B. Proceeding as above, we are getting these two results. Since A bar intersection Y is A and B bar intersection Y is B, A and B becomes closed in Y. Since A is the complement of B and B is the complement of A and B becomes both open as well. So A and B are disjoint, non-empty, open subsets of Y whose union is Y. Hence, by definition, A and B form a separation of Y. Next concept. If the set C and D form a separation of a space X, and if Y is a connected subspace of X, then Y lies entirely within either C or in D. Coming to the proof, let Y be a connected subspace of X. See, this is our space X and this inner rectangle, this is our subspace Y. Now I have supposed that the C and D, this part C and D form a separation of X. Since C and D are both open in X being part of separations, the C and D are now open in X. So this set C intersection Y, this part C intersection Y and this D intersection Y, they are open in Y by the definition of subspace topology, since Y is a subspace of X. Now, of course, you can observe from the diagram, the C intersection Y and D intersection Y, both are disjoint and their union is your space Y, that is subspace Y. If both C intersection Y and D intersection Y are non-empty, if both were non-empty, then what happened? Already they are open, disjoint, and their union is Y. So if they both become non-empty, the C intersection Y and D intersection Y, then by definition, they would constitute a separation of Y. But this cannot happen because Y is a connected subspace. Therefore, one of the sets must be empty. That is, either C intersection Y is empty or D intersection Y must be empty. So what happens? Suppose C intersection Y is empty. Then what happens? This Y should lie completely within this D, isn't it? And suppose your D intersection Y is empty. This part is empty. Then my subspace Y should completely lie within C. Therefore, Y must lie, the connected subspace Y, it must lie entirely within either C or in D. Next theorem. The union of a collection of connected subspaces of X having a common point is connected. So from this theorem, what we observe is the union of any collection of connected spaces need not be connected. So union of connected spaces is connected only if there is a point in common. Let us come to the proof. Let A alpha be a collection of connected subspaces of X. Suppose that P is the common point to all the connected spaces A alpha. That is, P belongs to intersection A alpha. Now to prove the space Y is equal to union A alpha is connected. So to prove Y is connected, we have to show that there exists no separation of Y. So assume the contrary. That is, C and D forms a separation of Y. So to prove Y is connected, I assume the contrary, that there exists a separation of Y constituted by C and D. Now the point P is in one of the sets C or D. Now the point P is in one of the sets C or D because C and D are disjoint because they constitute a separation. Suppose that P belongs to C. Then what happens? Since A alpha is connected, by previous lemma, we have just proved that if Y is a connected subspace and C and D constitute a separation of X, then the connected subspace Y lies entirely within either C or D. So by this previous lemma, it follows that A alpha must lie entirely in either C or D. But this A alpha cannot lie in D because A alpha contains the point P of C. See, you can observe here. Since A alpha contains the point P of the subset C, hence A alpha must lie in C for every alpha. So that union A alpha must contained in C. This union A alpha is entirely lying in C implies what? D is empty. But this is a contradiction because D cannot be empty being a part of a separation. Therefore, what we have assumed is wrong again. That is, there exists no separation of Y. And so the space union A alpha is connected. Next theorem. Let A be a connected subspace of X. If A is contained in B contained in A bar, then B is also connected. Coming to the proof, let A be a connected subspace of X and let A contained in B contained in A bar. To prove B is connected. So we have to show that there exists no separation for B. Assume the contrary, that is, suppose that C and D form a separation of B. See, this is our space B. Now the C and D form a separation of B. So by a lemma, which we have seen previously, that is, if C and D form a separation of a space X, and if Y is a connected subspace of X, then Y lies entirely within either C or D. So by this previous lemma, it follows that this A must lie. The connected space A must lie entirely within either C or D. Suppose that A lies in C. Then A bar is contained in C bar. But since C bar and D are disjoint, see, observe from the diagram, this is our C bar and this is my D. So the C bar and D are disjoint. Since B is contained in A bar, and now A bar is contained in C bar, now this B is contained in C bar. That is, B lies within C bar. But C bar and D are disjoint. This implies what? B cannot intersect D. B cannot intersect D leads to the concept that D is empty because C and D form a separation of B, and this B not intersecting D implies that D is empty. But this cannot happen because C and D form a separation of B. C and D form a separation of B. Therefore, our assumption is wrong. That is, there will not exist a separation of B. So the space B becomes connected. Thank you all.